Okay, hello everybody. Thank you for coming. I'd like to get started. I'm supposed to reiterate the point about not sitting in this room. We have fire marshal issues, so if you could please find a seat. If there aren't any seats, please stand. We don't want to get shut down. The other point that I wanted to make before we get started here is we're really looking for feedback. There is a site that I've now just hidden with my slides, but I'll put it up at the very end. It's havasec.com/io. And we're accumulating feedback about the talks here today. Please take a moment to fill out your feedback about this talk and about all the other talks you see here. Thank you. Okay, so this is writing real-time games for Android. This is the opposite of the saving battery life talk. I have a lot of stuff to talk about today, and it's kind of a lot of like random, seemingly unrelated topics. So I'm going to try to go through them as logically as I can. Hopefully, it'll make sense. Did you see that awesome fade? That slide totally faded in. I don't think I've ever done like a thing that has like a slide presentation that has fades and moving stuff before. So this is like a new experience for me. All right. So my name's Chris. I'm a developer advocate for Android. I work in Japan. My job is to advocate Android development. So please make something. I can help, maybe. If you're in Japan, yoroshiku onegaishimasu. Before that, I was an engineer on Lively. I worked on animation code, collision detection, server stuff, all kinds of stuff. Lively was our rather short-lived, but very cool 3D online world. And before I started at Google in 2007, I worked for about 6 years in the game industry. Shipped about 10 titles for GBA, PlayStation Portable, PlayStation 2, Wii. So I have some experience making games that are on other platforms. And today I want to talk about my experience making games for Android. So, I mean, obviously Android's a cool platform, and making games is awesome, so the two together just got to be awesome squared, right? But it's really easy to say that, and especially from, my perspective as like an employee of Google, it's really easy to say, hey, you should make games for Android, it'd be great, without ever knowing if it's really, feasible. And if I don't know how many people in the audience are game developers here, but the game developers will tell you that games are weird, right? They don't really fit into regular application development models very easily. They push your hardware in ways that your other applications will not. So I wanted to, in my position as an advocate, I wanted to be able to advocate, development of video games. But to do that with confidence, I need to be able to know that the platform is actually capable. So I made a game, and I'll talk a little bit about the game today. That I made. It's basically a learning exercise, but my goal is also to make a fun game. I'll release it when it's done, hopefully in a month or two, and I'll release all the source, and hopefully people can use that to build their own games for Android. So what I'm going to talk to you today is who cares about games? Who cares about games on Android? Why don't we just write like awesome friend feed connect Facebook apps or something, right? Like, isn't that where we're all going, right? So we'll talk about games a little bit. I'll talk a little bit about game engine architecture. This isn't really Android specific, but I figure that a lot of people in this room, and there's quite a lot of you today, are interested in writing games but don't have a lot of experience doing so. And like I said, game architecture from a code point of view is very strange. So I just want to a couple of slides about how I go about architecting games that I build, and how I very specifically which sort of architecture that I found worked well on Android. And then talk a little bit about writing Java code that's fast, like really, actually fast, on Android using the Dalvik virtual machine. And then some rendering stuff, drawing stuff officially, and then some tips and tricks. We'll get to the end. So who cares? Who cares about games on mobile devices? Well, everybody apparently, right? We have iPhone, where App Store, like #1 category of downloaded applications is games, and 79% of people have downloaded a game once. 100 million Nintendo DSs in the world, 200 million Game Boy Advances, and Game Boy, original Game Boys, right? I mean, and these are sold to an audience that is not necessarily just traditional gamers, right? I mean, you can find a lot of people who have a Game Boy Advance or a Nintendo DS in their pocket that, would never consider buying an Xbox 360 or a PlayStation 3 or something like that. So there's a huge interest in mobile games. And up until now, games on cell phones have not been, a really valuable proposition. And that's because before, say, the iPhone, cell phones were really not very well designed for games. Like the aspect ratio was wrong, and we had phones that for the longest time couldn't read more than one button input, or only had like a 92 color palette or some random crap like that. So right now we're getting into systems that are portable, they're high powered, they're able to host real games. And by real, I mean like modern game design kind of games that people want to make and play today, not games that were popular 30 years ago. And we also, I think, are seeing a convergence of people who are interested in having a cool phone and also playing games, even if they're not what we would consider the traditional hardcore gamer market. I'm not going to use the word casual in this talk. So as I said before, game tech is really specific. Another reason to do games on Android and on any platform, I think, is a stress test. And if you can support games, and you can support a lot of different types of games, then I think that your API is probably going to be able to support all kinds of other media applications. So why games on Android, right? This is the one slide I'm going to spend on this. I have this really long, involved rant, like invective-filled spew that I would like to give to you about what's wrong with the current game industry, but I'm not going to do that. I'm just going to give the little 30-second one-slide version. And that's that basically the traditional game industry has been built, especially in the last, say, 10 years, around marketing games towards a very specific audience. And that audience is an audience that really appreciates advances in technology. It's also an audience that has a lot of disposable income. So we've seen games that sell well also being correlated with games that have really nice graphics tech or have really impressive technical features. But what has happened because of that is that audience has become the only viable audience in the minds of a lot of game developers. And so we have consoles now that are extremely powerful computers and cost $200, $300, $400 when they launch or more. And they do produce fantastic games. I don't have anything bad to say about those games. I love them myself too. But you could make a PlayStation game for $5 million, a PlayStation 2 game for $5 million, and you make a PlayStation 3 game or an Xbox 360 game nowadays, and you're talking about what, 20, 30, $40 million, right? I mean, we're very carefully or very quickly moving into a space where the platform is becoming less and less able to support itself on its one market base, which is the sort of the hardcore gamer, right? And we do have alternatives, right? We've got like Xbox Live Arcade, and we have Nintendo Wii and the DS and the iPhone, showing that there is a market for games that are not about muscle-bound like space marines who have amnesia or mysterious past, right? Like, if you are into muscle-bound space marines with a mysterious past and you really like guns that are also chainsaws, there's tons of games for you, right? That's great. You're the target audience. But there's a lot of other people out there who might get a game about something else. And the game industry doesn't really make games for them anymore. They used to, but now it's too expensive, right? So even if you made $50 million on a video game, you're going to not do anything new, right? You're going to do whatever sold last time because you spent $50 million. There's nowhere you're going to take any risk. So what we've seen is a contraction of viable genres. And that's not good, right? I mean, games are awesome. They should be enjoyed by everybody, and we should be able to make whatever we want. Right now, the current marketing conditions mean that 10% of professional game developers make a profit and everybody else goes out of business. So I think that, and this is like I said, the end of my little side rant here about this. Mobile games in particular, games that are being distributed over digital distribution services like Android and like iPhone and Xbox Live Arcade and those types of systems can solve this problem, right? Because we can give developers a means to develop games that are much, much lower risk to developers. And lower risk means more interesting and diverse content because you can take a risk. You can make it, do something that's experimental. You can do something that you'd never be able to do in a $15 million game. Right? So I think that Android is particularly well positioned from this point of view because we have an audience of people who want a cool phone and also want to be able to play games and do things on it. As we saw in the previous slide, portable gaming is a big deal, and all of you are here, and they put me in the really big room because clearly people care about games, right? But on the other hand, we also have always-on internet connection, and we have an internet-savvy audience, and that's a combination of things that we haven't actually seen very much of in the past. iPhone's certainly doing it too. I think that Android can be right up there in this sort of sea change of allowing new or maybe previously retired gamers to come back. So, advance. So, why, what kind of game did I make, and why did I choose to make that game? I had 3 goals when I started out, and I have to tell you, I worked on Lively until about October of last year. I moved to Japan in October of last year, and I started working on this in very late November. So, and this is a 20% project for me. I work on it 1 day a week. So this is not my full-time job. So I needed a game that I could actually complete in a good amount of time, that I think I could make fun. I don't see any reason to make a game if you're not going to make it fun, right? So my number one goal was to make a fun game in the sort of time that I had with the constraints that I had. My number two goal, as I mentioned, was to reduce open source. I think that a lot of people would make more games if they knew where to start. And if I can provide some code or some framework or some documents or some blog posts or something saying, like, here's how I did it, maybe that's a jumping off point. And even better, down the road, if other people could take that code and make new games out of it and release their source as well, then I think we could have a really pretty awesome community, right? And then, as I said before, I want to stress test platform. So I went for an orthodox 2D side-scroller. Assuming everybody knows what that is, but just in case, that's Super Mario Brothers, Sonic the Hedgehog, games like that. We have basically multiple layers of images that are scrolling at different speeds. It's called parallax scrolling. They're built out of tiles. We have little small images that get put next to each other to build the worlds, right? It's pretty traditional, very, very popular in the mid-early 90s. Genre, recently underserved, I think. Nice thing about this particular genre is I felt that I could do it in 6 months. I made a bunch of side-scrollers when I was working on Game Boy Advance games. I have some experience with them, and I quite enjoyed the genre myself. So it felt like something that would be fun to make, something that I thought the people would enjoy, and also the correct scope. It also pushed the right buttons technically. I need to know how to do input systems correctly and sound, and I need to be able to draw with OpenGL or Canvas or whatever it is I'm going to do that any game is going to have to know how to do, whether or not it's 2D or 3D. So then the stuff I'm going to talk about today is a little bit focused on 2D, because that's the kind of game that I made. I suspect that a lot of it will be completely applicable to 3D games as well, especially the stuff about using OpenGL quickly. So please don't take this as being absolutely just for 2D games. I want to talk about games in a general purpose case, but I'm going to use the 2D game that I built. Okay, so let's talk about some game engine architecture. Before that, I had a picture of a guy holding a chainsaw gun here, but legal made me take it out. Sorry. I've just put the little text in instead. I didn't really, own the license, I guess, so they're right. So I just want to have a really quick demo here. This is the game that I'm working on. It's called Replica Island. It's getting close to being done, and it's probably about alpha. I have a very low-quality video to show you. And it's really hard to shoot video on the Android device that I have. So I apologize. And it's also quite difficult to play a video game while shooting video on an Android device and keep the screen from getting screwed up. So I just have a very short clip, and it's not really representative of the entire game, but it'll give you an idea of what I'm talking about, an idea of what the scope is that I'm working on, and hopefully you think it looks cool too. Let's see if I can make that play. I think I have to click again. There we go. So we got, the Android robot, and he's blowing some guys up and crushing some robots. And he's going to take this robot over here with this little red ball. Now he's possessed him. Now a guy can walk over here. This is a test level, so there's not really anything to do in this level, but the robot can walk over here and then self-destruct to go back to Andrew. So the goal is to collect the 3 gems in each level. You can get coins and things like that. There's some power-ups to acquire and a lot of robots to crush, people to talk to, things like that. And it's a pretty traditional side-scroller, I think. Oh, and here's a character we could talk to, but I think we're just going to run by her instead. And you can kind of see, that there's a couple of layers of background that are scrolling at different speeds. This is a parallax talked about. We'll talk about that a bit in this talk. Okay, so there's the 3rd gem. Hooray, we completed the level. So that's Replica Island. Thanks. I hope you guys enjoy it when it comes out. I'd like to hear your feedback. So I want to talk a little bit about how I build games, just generally. And this sort of general architecture is the architecture I used to build Replica Island. It's also very similar to the architecture that I used to build a Spider-Man game on PlayStation 2. So I believe that it scales pretty well. My approach is to, we have the same kind of problems that we have to solve in all games. And that's that you have this sort of world full of objects that need to be simulated with time, right? We've got, the character moving around, and there's other things, and they're going to collide, and they're going to pick up stuff and hit the ground and bounce, and then they're going to have velocities that need to be calculated, and also animations that need to be updated. These are all sort of taking a time step, a simulation step, and then updating and then figuring out the results. That's sort of the basic problem that most games face. So what I do is I have a game graph. Basically, we can think of it as a tree. It's technically a graph, but you can think about it as a tree for most cases, where the root node is the main loop. And all the child nodes under that root are things that get updated every frame by the main loop. And those things can have their children, and those things can get updated every frame as well. And halfway through the tree, it's okay if we start adjusting the way that things below in that particular subgraph get updated. For example, we could have a main loop that has a game object child, and a manager as a child. And that manager is going to be the thing that manages all, say, like the sprites for bad guys on the screen. And the thing about bad guys on the screen is you don't really care about what they're doing when they get far enough away from the camera, right? In fact, you'd like to stop processing them completely when you get far enough away from the camera because they're going to slow stuff down. If you've got a huge level and there's like 500 guys in there, but there's only 3 that are actually close to actually being able to interact with the player, and you only want to update those 3, right? So in the game graph context, the game manager node can sort its children by visibility and only visit the children that it thinks are close to being visible. That's kind of how that concept fits into the graph. And then game objects themselves, which are an enemy or an explosion or the player. Those things are subgraphs of the game graph as well. The sort of initial implementation that I started out, sort of the naive implementation when I first joined the game industry, was to take make a game object class and then derive that and make visible game object class and implement the rendering part, and then derive that and make a moving game object class and implement velocity calculation, and then derive that and make the rendering the collision detection game object, and then derive that and make the player out of that, right? And that actually works for a while, and then eventually you get into a case where you need functionality from step A and functionality from step C, but you don't want the class in the middle, and then you're sort of screwed, right? So what I've been doing for the last couple of years is sort of an aggregate object model where I have a game object that is just a list of other components. And each component is a single piece of functionality. It updates like a single update loop that says, I'm going to do something, like move the player or render the player or take the input from the device and then decide how to adjust velocities. And it only does one thing. And the nice thing about that approach is you only insert the components into the object as they need it. So the player happens to need to know how to read the input, but the enemies, until they get possessed, don't need to actually read the input ever. So they don't have to have the input component. And if I decide to possess an enemy and suddenly I want him to respond to the input component, I can just stick a new component into his game object at runtime, and it suddenly starts working. So this is actually an important point. And the reason I'm sort of belaboring it is that it also is very helpful because it helps you not execute code that you don't need to do. And not doing extra work is going to be a recurring theme in this talk because optimization is going to become a big problem for us when we start to write games. So let's just go to the graph and see what this looks like. This would be like the top level view of like a very simple game graph where we have a main loop and then we have some other systems as children that get updated every frame. I just want to give you an idea of how I do this. This isn't the only way to do this. This is just the way I do it. So here's an example with 2 objects in the game object system. The background object was the thing that's drawing the backgrounds and the layers, and then the player object would be like the player itself. And you can kind of see how they're made up of components. They look like children in the graph because that's really what they are. So for the background, there's like 3 layers. There's I think if you saw it in the demo just now, there's like the blue static background, and then there's a midground layer, and there's a foreground layer as well. So for each of those layers, there's like a scroller component and a render component. Scroller component figures out how much it's supposed to be scrolled, for the current, based on the current camera position, and then the render component says, okay, now go render this frame. And then the player is made up of a bunch of stuff like physics and animation and rendering and gravity and movement, things like that. So actually, this is actually pretty close to the way that Replicon works right now. It's a little bit of a simplification. But you can see that every frame, if we want to update this game and produce a new frame showing one more simulation step of the game, all we have to do is traverse this graph. And the order in which we traverse these things, is sort of important, so I just sort of say breadth first, left to right. Anyway, that's how I do it. You can do it however you want. But I wanted to sort of say, think about this kind of stuff when you start writing video games, because if you don't, it'll come back and bite you later. It bit me on production games that I did in my previous job several times until I stopped doing it that way and started doing it this way. Important point about this is that the graph takes time, like the delta from the previous frame, as its input. Its output is a bunch of things to draw for the render system, but its input is time. And the reason that's important is that any sort of temporal logic that you're going to do in a game for a system like Android needs to be scaled by time. So that means velocity calculations, animation duration calculations, anything that's related to time has to be scaled by real time and not, like, say, frame counts. It's really easy to say, oh, I'm going to add 5 to my velocity, or I'm going to wait for 3 frames and then play this other animation. And the reason you don't ever want to do that is you don't know what the duration of each frame is. You might think, well, I'm running at 60 hertz, but Android is a multiprocessing OS. You have no idea what's going on in the CPU. You have to plan for a variable frame rate. And what happens when you don't plan for a variable frame rate is when your frame rate's really low, your game kind of falls apart, slows way down. And you also start to experience sort of temporal anomalies as the frame rate fluctuates, like your collision detection will cease to work and things like that. So very important point is that, and that a lot of people would not maybe think about if they've not written a game before, is to take time and do all the calculations you need to do related to time with real time. It's okay if you bias the time. You want to have a slowdown matrix effect? Sure, go for it. Just don't use frame counts as your... The other important point is that the traversal of the game graph doesn't actually draw anything on the screen. It just produces a list of things that we might draw sometime in the future. And that's important because of the way that it's particularly important in kind of all kinds of games. But for Android, it's important because of the way that rendering works. And this is true whether or not you use OpenGL or you use the Canvas system to be doing your drawing. You're going to hit a point at which the rendering thread is going to block on hardware. And the reason that happens is that the hardware may not be done drawing the previous frame. If the hardware's not done drawing the previous frame, it's not going to let you do anything until it's finished. So if you're using OpenGL ES and you call EGL swap buffers, that's going to block, and it could block for like 16 milliseconds, right? And the CPU is not really doing anything when that thread is blocked, but it means that your game is not proceeding, right? So it's important to split the game logic from the rendering layer. And the way that I did it for Replica Island is I have 3 main threads. The main activity is what I call the UI thread. It's just when you make an Android application, you make an activity and it comes up and it produces your views, and then it can receive input events. That's pretty much all it does. That thread's mostly dormant. It bootstraps the game, and then it's pretty much done. Excuse me. I have a game thread, which is where the game graph lives. It gets updated as often as it can. And it produces a list of drawable things to hand off to the rendering thread. The rendering thread is basically a surface holder. If you look at any of the OpenGL examples that are shipped with API demos, or in a few minutes I'll talk about a sample that I wrote that you can look at as well, you'll see classes like GL Surface View, which was part of the API demos in previous versions, now part of the API in Android 1.5. But it implements a separate rendering thread, separate from the main thread, that just sits there and talks to OpenGL as quickly as it can. So basically we have this game thread producing a list of things to draw every frame, and then the rendering thread consuming this every frame. And the nice thing about this is that means that the frame rates of these 2 threads are decoupled. If the rendering thread slows way down because I just threw 100 sprites at it, then as it's chugging on drawing those 100 sprites, the game thread can continue to run at 30 hertz or 60 hertz or whatever. If there's a backlog the other direction, like the rendering thread is starved, it'll just re-render the frame that it had previously, which is not ideal. I mean, you don't want to drop a frame if you can ever avoid it, but the screen doesn't go black, nothing blows up. You can pause the game and just by turning off the rendering or the game thread, and the rendering thread will still continue to draw stuff on the screen, whatever it had last. So I'm sure there are other ways to do this. This is how I did it at Replica Island, and it worked out pretty well. Okay, so let's talk a little bit about writing Java code that's fast. Before I start talking about this, I'm going to offend all of the Java engineers in the room, and I apologize for that. Also, when I say Java, I mean Java on Android running the Dalvik virtual machine, not any other kind of Java. So please don't kill me. Basically, I'm a C++ engineer. In fact, I never wrote a line of Java in my entire life before I started this game. So you should probably take everything I have to say about Java optimization with a kind of gigantic grain of salt. But I also think that most Java applications don't really need to be optimized at the sort of level that I've been working. It's because, for the most part, you have this language that, provides a bunch of awesome services for you. It provides an awesome standard library. You've got memory referencing and all this other stuff that you don't get in languages like C++. And that's why writing Java applications is easy and cool, right? And then maybe, I'm sure that everybody does sort of macro-level optimization of their algorithms and not doing a order n squared, search when you can do a n log n search and stuff like that. But I'm going to talk about optimizations that are a little bit more low level than that. And I think that might be something that Java engineers don't generally have to worry about. So hopefully there's some useful information here for you. That's one bullet point that says writing real-time games is an exercise in finding the perfect balance between flexibility and performance. That's like a whole talk in itself, that topic. But basically what I want to say real briefly is that at some point you're going to have to choose between absolute performance and the ability to make the game. And making games is about iteration, right? What you're going to do if you sit down to make a game is you're going to have an idea and you're going to make it, and you'll write it and it'll be great, and then you'll give it to somebody else and they'll have no idea how to do it, or they will not find it fun at all, and you realize that there will be all these usability problems with it, and so you'll iterate. And that's how games are made. And the games that are really good are the ones that iterated for a really long time. That's sort of the general rule, right? In order to iterate, you need to have your code flexible. You need to be able to go in and make changes without injecting bugs. You need to be able to swap out one piece for another. You need to be able to write tools that can generate data that then the game will use. You need to have a bunch of infrastructure. But infrastructure often comes at the cost of performance, right? As soon as you have all your game serialized into XML, then you have to actually load that XML and walk through all those objects, and that's not really fast, right? So at some point, you're going to have to choose between flexibility and performance. And basically, I always err on the side of flexibility until the game starts to slow down, and then I have to go back and do performance tuning. And the reason is that if you can't tune the game, it's not going to be fun. And there's no point in making a game that's not fun. The corollary to that is if you make a fun game that runs at 1 frame per second, nobody's going to play it. Right? So it's not all one or the other. But if you have to choose, my general advice is to stay on the side of flexibility and then go back to performance when you need it. And to enable that, my approach here, which has served me very well, is to just implement everything as simple as possible for the first iteration, but keep all the hooks there for swapping things out. So it's okay to do that order n search the first time. And when that order n search shows up on your profiler, then it might be a pretty good time to go back and replace it with something smarter. And when you wrote that order n search, hopefully you wrote it in such a way that it's very easy to replace without the calling code knowing anything about it. So then that leads me to the last point about this topic, and that's profile early and constantly. And we have a bunch of profiling tools I'll touch on in a little bit later, but if you make a thing that accumulates the amount of time that you're spending per frame and spits it out every 3 seconds to a log, that's fantastic. That's all you need. You can write that in about an hour, and you can hook it up into all your game systems really early, and you should do that. And you should have a constant understanding of where you are in your game frame rate, because if you wait until the last minute to go look at why your game is not fast enough, then you're going to be screwed. It may be the case that you have just one system that's a repeat from 1 equals 1,000 or something. But it may also be the case that it's a death from 1,000 cuts, right? And that you don't have any one system that you can optimize. And that's a really difficult position to be in. So I say, print your profile out really early and keep looking at it and keep understanding, what you're doing. One comment that I would like to make about this point before I go on is that don't print your profile to the screen. I see a lot of developers that make this mistake. Because it's really easy, especially in Java, I think, to mess up printing to the screen in a way that will actually affect the output. Right? You can very easily hurt your frame rate by printing it on the screen. And also, it's not information that you really need to see all the time. A heartbeat every 3 seconds is sufficient. I had one guy that I worked with who had been working on improving his frame rate for his game and had gotten progressively faster and faster and faster, and then he'd hit a wall, and he couldn't figure out what it was, and when he went and looked at it, it turned out that all the string concatenations he was doing to print the frames per second counter out on the screen were causing all these allocations to be created, which was causing the GC to fire all the time, which was slowing him down. So just a point of caution. Okay, so let's talk about ways to use Java that are not very flexible but are very fast, given that I gave you the flexibility talk. Don't ever allocate memory. Okay, you can allocate memory, but don't release it. That's a little extreme, right? But what's going to happen is when you allocate memory, every time you allocate memory, the GC gets a chance to run. Right? And the GC right now, under Android 1.5, can take 100 to 300 milliseconds, even if there's nothing to actually do. It has to walk the whole object map, right? So 300 milliseconds at a 60 hertz game, I mean, the user's going to feel that. That's a third of a second, right? The user's going to know that the game just stopped, and that's absolute death for real-time games. If you remember the video I just showed you, if the robot's jumping over a pit and the game stops and then he falls into the pit, that's a bad game, right? The player's going to stop at that point. So you don't ever really want the GC to fire. So, okay, go a little bit less extreme. Allocate all your memory up front. Allocate all your memory at a time when gameplay is not going on. And don't allocate and don't release while gameplay is actually running. And memory pools are your friend. This is not actually a very hard problem to solve. In non-Java languages, we have to solve this all the time anyway. So just make your memory pools, pre-allocate all your objects, reuse them, don't actually release the references. And when you are at a point that you can pause, like in between level load or at a pause screen or sometime when the game is not running the simulation at full tilt, that's when you should manually invoke the GC. There's a command, I think it's system get runtime invoke GC or something like that, and it will you can cause it to run whenever you want. Otherwise, you don't know when the GC is going to run, right? You can't really predict it. It's based on whatever parameters it uses and how often you allocate memory. So beware of memory allocation. Also, we have this pretty fantastic tool that ships with the Android SDK called DDMS. And it will allow you to track allocations pretty much in real time as your application runs. So you can run your game on your device and have it plugged in, and you can boot up DDMS. Actually, there's a tab in Eclipse for it now even. And you can hit start tracking allocations, and when you hit stop, you'll get a list of all the allocations that occurred in between those two button clicks, right? And what you're going to find out is that Java allocates memory all the time in places you would never expect. At least I never expected. Like, you ask for the array for an enum, like enum.values, yeah, that allocates memory. And you use a hash map or an iterator or anything from collections, that allocates memory. Arrays.sort, really fast, but duplicates the data set that it works on. Any kind of like system library function where they want to give you back an immutable reference, but there's no such thing as an immutable reference in Java, so they have to copy it, right? You can really easily find out that you made a lot of mistakes. I had to go back and rewrite a bunch of my code after I started using DDMS. So DDMS is fantastic. What you can do is you can reduce all of the allocations that you do yourself in your own code. Some of the stuff that Java is doing is not going to be avoidable, and that's okay. We don't actually need to get rid of 100% of allocations. We just want to get rid of like 90% of them. So having a little bit of like, say, string concatenation or a little bit of stuff that you can't stop anyway is fine. It's fine. You don't have to worry about it. You only really what you want to do is keep the GC from running frequently. If it runs once every 5 minutes, that's still much better than running randomly every 30 seconds or something like that. So my approach is basically to treat Java like C++, and this is the point where I said I was going to offend everybody. This completely flies in the face of the language design, which I completely understand and I sympathize with. But if you want to make a fun game, making a fun game and having it actually be fun to play is more important, I think, than the language purity. So you can't really use collections. You can't really use enums. They're a really bad idea anyway, from a lot of different reasons. Like I said, arrays.sort, allocates memory. Stuff like reflection, get class names, things like that. You can use these functions, but not as the game is running. And it's not like you have to completely ban them, but what you have to understand is that every time you allocate memory, or every time one of these functions allocate memory, the GC is getting a chance, right? So I just avoid them completely. And actually, once you're cognizant of this particular problem, it's pretty easy to avoid. As far as I know, I've not gotten the GC to run during Replica Island gameplay in about 5 months. So I kind of have these slides here just to let you know sort of the extent of the problem, so that when you go to write your games, you can code appropriately. But absolutely use DDMS as your tool to find out where allocations are coming from, because it's fantastic for that. Also, like I said, I'm not really a Java engineer. I just sort of play one on TV. So I'm sure the rest of you could come up with much better solutions than I did, like replacing implementations from the standard libraries with ones that don't do allocations at runtime or come out of a pool, and those might allow you to go back and use some of those standard library things without having to rewrite your own things or whatever. I don't actually know how to do that. Okay, so step 2, don't call functions. Okay, you can call functions, but you have to understand that functions are not free. They kind of don't teach you in school, at least when I went to school. They didn't really ever touch on the fact that functions might be expensive. And in fact, in Java, they're pretty expensive depending on what kind of function you're calling, right? don't ever call interface functions. Those are really slow. Like you call a function through an interface, it has to go through an extra lookup or something. There's 30% overhead. At least that's about what I calculated. You know, your mileage may vary. But like accessors and mutators, my bestest friends in C++, don't really belong in your inner loop in Java because you want to avoid, anytime you're in a time-critical piece of code, you want to cut down the number of functions that you're calling. So if that means calling something once and assigning it to a local variable and then using that for the remainder of the function, that's great. If you can assign that local variable at bootstrap and then never call that function again, that's even better, right? This is what I was talking about when I said death by 1,000 cuts. If you architect your game in a way that you would architect any other sort of regular application, you probably end up with a lot of general function calls. Get this, set this, put this over here, right? Yeah, you call those things a couple 100,000 times per frame, and that's the end of your frame rate. And then what are you going to do, right? It's not very easy to go back and change all your functions, right? So beware. You also have to be a little bit wary of JNI functions. JNI is a Java mechanism for calling into native code. And actually, the nice thing about it is, you're executing native code. Native code is really fast. So the contents of the function are really fast, but actually calling it is actually kind of slow. There's some pretty significant overhead that occurs when you actually need to invoke a native function. So in particular, like if you're calling OpenGL stuff from inside of Java, all those gl.glxx functions, all of those are JNI functions, right? And it's really easy to get up to several hundred, OpenGL calls a frame for a pretty simple scene. So this is something you should be cognizant of. And one thing that you may end up having to do, that I've had to do in a couple of cases, which as a sort of programmer really offends me, is just make fields public. And like, that goes against every, kind of grain in my body because I want to be a defensive programmer and I don't want to, write code that is susceptible to easily injectable bugs. But on the other hand, gameplay is king, right? I mean, there's no point in making a game if it's not going to be fun. And if you find, you run your profiler, like I told you to, and you find out that accessing this one field, like the position of the player, for example, is happening, 100,000 times a frame, then you could, you might be able to get some pretty serious time back by just making that field public. Here's a graph. It's not a very scientific test, so I didn't put any numbers on the graph, but I think that the sort of relative cost of these types of functions is correct. Basically what this means is you call a local function or you call a function from a derived class or you call a virtual function in Java. It's all kind of the same cost. You call an interface class, you all of a sudden incur this sort of 30% mystical overhead. And then you call through JNI, the overhead's even higher. Just to illustrate what I already said. Okay, so a couple other tips about Java, and then I'll shut up about it. Local variables are your friend. Even better than member variables are local variables. Use them. Use the final keyword anywhere you can. That's like, I think CS 101, but I thought I'd reiterate it anyway. The G1 and other Android hardware devices at the moment don't have an FPU, so if you do any kind of float math, that's going to be done in software by an FPU emulator. So if you're really interested in absolute performance, you could consider using fixed point math. I actually don't care this much. This is a point where I chose flexibility over absolute performance. I just go ahead and do the float math. And it's really hard to gauge how much that costs me in terms of my frame rate, but I don't believe it to be very high. Another point that is sort of unique to unique to Android is that the regular Java printf mechanism, systemout.print, I guess, is actually fairly slow, and you should use log.d or log.e or one of these other log equivalents that we give you to print out to logcat, because it's way faster. And that's another example of where you could unintentionally sort of screw your frame rate when you're just trying to produce logs. And then use traceview. I mean, this is the best part. We ship a pretty full-fledged profiler with the Android SDK. And even better, you can turn profiling on and off with just this little function call. So you can make like a menu item in your little menu that pops up that says, toggle method profiling. And that will let you go to some little spot in your game that you notice appears to be slow and turn on, method tracing right at that spot. And as soon as you turn on method tracing, your frame rate is going to fall through the floor because it's really expensive. But you can, generate this trace file just in the area that you're interested in, and then go back and look at it in traceview. And the numbers for like how long it actually took to call a function, you should probably just ignore those because method tracing is on, and the actual seconds value is probably not very useful. But the number of times that a particular function was called, and who its parents were, and who its children were, and what percentage of the total time they were, that's super valuable information. And you get these cool graphs too, right? So absolutely use this tool. From a game development background, the fact that we actually have this tool is really great. Usually we write this stuff ourselves, right? Okay, so let's talk about rendering. This is a screenshot from this sample that I wrote. I alluded to it earlier, called Sprite Method Test. And what it does is it just tries to draw sprites on the screen really fast and sort of animates them and bounce them around. And what it does is it lets you choose. There's a bunch of different rendering mechanisms in Android that I'm going to cover in a minute. And it lets you choose each of them, or a subset of them, and run the same test with pretty much the same output, and then compare the results to see, what's faster. So this is what it looks like if you run with 1,000 sprites on the screen, and you use the Draw Texture OpenGL extension, which is available on the G1. And with 1,000 sprites on the screen and a background, it runs about 10 frames a second on the G1. So, and I'll put the URL out for that so you can test it yourself on your new devices at the end of this part. So basically, you have two methods for drawing on Android. The first is Canvas, which is a very slick, very easy to use software-based drawing mechanism, which is how most of the Android UI is drawn. It's pretty easy to get into Canvas and start drawing lines and making things and copying images in there and rotating them. And actually, considering it's all done on the CPU, it's pretty fast. If you don't have a lot of drawing to do, like, for example, in the Sprite Method Test case, under about 10 sprites, easily hit 60 hertz just using the software implementation. Don't have to worry about OpenGL stuff. And Canvas is by far the easier of the two mechanisms to use. It's easy to set up, it's easy to tear down. There's already hooks for it in the main thread if you don't want to make a rendering thread, although I'd recommend you do. So if you're making a Bejeweled clone, you can make something more interesting than Bejeweled, right? But if you're making a Bejeweled clone, Canvas will probably meet all of your needs. Then the other option is OpenGL-ES. So obviously you can use OpenGL for 3D drawing. You can also use it for 2D drawing. It's accelerated on platforms that have hardware acceleration, like the G1. And other platforms in the future, if they don't have hardware acceleration, like, for example, you run in the emulator, then there's a software renderer that is supplied. It does scale to much more complicated scenes than Canvas, because the actual composition of the frame is done in hardware, and the hardware is pretty good at doing that. So you can get 1,000 sprites on the screen at 10 frames per second in OpenGL. There's no way you could get it anywhere close to that speed in Canvas. It's considerably more complicated to use. There's some setup and tear down. You've got to copy your textures into video memory, and you have to watch out for the case where your video memory got trashed because another application came up in front of yours, and then you have to reload your textures, things like that. There's a little bit of work to do for the setup, but then once it's up and running, the actual API to draw things is not that much more complicated. So with OpenGL, we get actually a lot of different ways we could draw things in 2D. The easy, most basic case is just to make like a 2D quad, just a square of verts, and put a texture on it, and just draw that using an orthographic projection. And that's like the OpenGL 1.0 or like 101 type of approach to drawing sprites. And that works. The other way is we could use vertex buffer objects, which are basically exactly the same thing, except you take that vertex buffer that describes your little square, and you throw it on in video memory. And then it doesn't have to get sent down the bus every frame, and the card just has it in memory, and it's already in a native format, and it can draw it faster. The thing about VBOs is that they're not actually supported as part of OpenGL-ES 1.0. And Android guarantees OpenGL-ES 1.0, but not anything above that. So if you want to use that type of extension, it's available on the G1. You need to check to see if that extension exists, because you could be running on some future device that we don't know about yet that doesn't actually support that extension. And how do we choose which extensions are supported? Well, we don't. The people who write the OpenGL driver for the specific device get to choose, right? So the G1's extensions that actually supports quite a number of extensions, are all based on what the driver that Qualcomm supplied us supports, right? So whenever you use any kind of extension, with VBOs, I'm going to talk about draw texture in a minute as well, you need to test the GL, I think it's GL get string GL extensions. I have that in the next slide, I think. That will just be a string of the extensions that are supported, and you need to grep that to make sure that the functionality you want to use is actually available on the device you're running on. If you don't do that and you run on a device that doesn't have that thing, your game's going to crash, right? Fortunately, for something like VBOs and quads, the actual interface is so similar that it's pretty easy to write your code such that you can fall back on the 1.0 implementation if the 1.1 one doesn't exist. And then there's the draw texture extension, which is another extension that you have to check existence for. And what it does is it sort of just blitz textures to the screen. It's very fast. The disadvantage to the draw texture extension is it can't do rotation, I think. So here's a graph of the relative speeds of these drawing mechanisms. This is basically straight output from that sprite method test. At 10, what we have on the left side is the number of sprites that it's drawing, and on the bottom axis is the number of milliseconds it took. And you keep in mind that 16 milliseconds is where you have to be in order to get 60 hertz. 32 milliseconds is where you need to be 30 hertz. So anything slower than 32 milliseconds is probably going to be an unplayable real-time game, unless you're making a game that isn't really that real-time. So, faster is better, right? So if we look at 10 sprites, all of them are pretty much the same. And the reason they're all the same is that, like I said before, the hardware is going to block on the page flip, right, on the previous frame completing drawing. So with 10 sprites, all of these methods, draw texture and VBOs and the basic quads and canvas, can actually generate the frame in probably less than 16 milliseconds, and then the remainder of the time comes from the hardware blocking. When we get up to 50 sprites, you can already see the canvas is starting to take off, right? It's already starting to slow down. And you can see real dramatically as we get up to 1,000 sprites that canvas is totally hosed. Actually, the basic quads approach is totally hosed too. This is on the G1. It might be different on other platforms, but on the G1, that's almost as slow as canvas, even though it's hardware accelerated. VBOs actually hang in there pretty good. They're easily twice as fast as the non-VBO versions of the same quads. And then draw texture just totally kicks ass. It does slow down. I do drop down to 10 frames per second when I have 1,000 sprites on the screen, but 10 frames per second is only 90 milliseconds. It's way better than 362 milliseconds for canvas. So short answer is you should use draw texture, right? Especially if you're making a game that's 2D. For Replica Island, I use draw texture for all of the sprites on the screen, and actually talk about how I render the background. I experimented with draw texture for that as well. And here's that thing that I already said. You must check this getString GL10 extensions before you start using these extensions. Otherwise, you won't be future-proof. However, like I said, Canvas is really easy to use, and it might be a total win for you if you don't have to update things every frame, or you have a type of game where you have very few things to draw every frame. Because for small data sets, it's more than capable. So this is the URL for the sprite method test that I've made. If you got a version of it before about yesterday, it actually contained a bug that I'm going to talk about at the end of this talk, so you should grab the source again. But it's up on code.google.com, and you can download it and you can look at it. And it kind of provides a framework also for how you might build a 2D game. It's very similar to what I ended up writing for Replica Island, but it lets you, sort of generate an activity, then just swap out the rendering mechanism pretty easily using the same sort of simulation code. Okay, so I want to talk a little bit about how I drew the backgrounds for Replica Island. And the reason that I want to talk about this is that background drawing ends up being the most expensive operation in drawing my frame. It's more expensive than drawing the sprites. It's more expensive than calculating my collision detection. It's costly. So the way Replica Island works is there's these 3 parallax layers. One of them is just a static bitmap. It's actually slightly larger than the screen, so it scrolls, but very slowly. The second is a midground layer that scrolls at some speed slower than the main camera to give the illusion of depth. And the foreground layer is kind of what the character is standing on. It would be nice to have more layers, right? Because then I could have like a layer in front of the character, like a shadow layer or some trees that go in front of you or something like that. But at this point, the game is not quite fast enough for me to increase the number of layers without having to decrease something else. So if I decided to trade the number of enemies I'm going to put on the screen for another layer, I could do that. But given the sort of game fidelity that I want, I decided to cap it at 3 layers. So each layer, besides the very background one, is drawn out of tiles, these little small 32 by 32 pixel squares, right? And those are reusable. And the reason to do it that way is that then you can have levels of any size, right? Your level just ends up being this big array of tile indices. And all you have to do to draw is figure out which part of that array you're looking at, given the camera, and then just go draw those textures in the right spot. So you're not limited by the size of VRAM. You're not limited by the size of main memory. I guess you are. But the actual tile map is very small, and the actual level maps end up being very small, like 4K. So you can make levels of pretty much any size. The bad part about this is that if you're going to draw a layer that is completely full of tiles, that means you're going to make like 150 calls to this like draw texture extension or whatever method you choose to use, because each one of those tiles has to get drawn. And 150 calls to OpenGL, just right there, based on the previous slide, you should know that those are all JNI calls, and no matter what they actually do under the hood, I'm incurring some cost to call those functions 150 times per layer. And I have 2 layers that are like this, so that's 300 calls per frame, right? That might be pretty costly. The other thing that I actually did not run into, but you could run into on this type of thing, is that some GL implementations will have a fixed amount of command buffer size, and if you overflow that, then it's going to start drawing before you're finished. Actually, I never hit that, but having that many GL calls for my sort of rather simple frame seemed kind of wrong. So I tried a bunch of different ways. Here's what those layers look like. There's the background image, and then there's the midground, and there's the foreground, right? I tried to render these a bunch of different ways because it's pretty slow, and I wanted to make it better. And this is what they look like when they get composited, right? So I started out with a really simple approach, and that was just to take this thing called an atlas texture, which is just a texture that contains all of the possible tiles in this particular level, and then use this draw texture extension to draw all the tiles individually. And what I was going to do is I was going to select tiles out of this texture map by using the GL parameter function, which allows you to set cropping on a texture, right? So I just, bind the texture once, and then set the crop and draw, and then set the crop and draw, set the crop and draw, right? This is a terrible idea. It totally worked. I mean, it produced the output that I expected, but it was really, really slow. And I should have guessed that it was going to be really, really slow, because it turns out that GL texture parameter is a pretty slow function to call, and that this produces a lot of state change. And if you ever worked on fixed function hardware like this is, state change is expensive. Any kind of state change that you are going to apply. I mean, binding texture could be expensive, right? So you want to avoid as much state change as possible. And this is a huge amount of state change, right? So, boy, this did not work. I mean, it looked all right, but it was really slow. So then I decided, well, instead of using this atlas texture thing, I'll cut it up into individual 32 by 32 textures. And then I'll just call draw texture for those things, and I won't ever have to change the state of the texture itself once I've loaded it. Actually, this works pretty well. You have to make some adjustments to the way that you draw, because if you're going to, if you have a loop that's walking over like a 2D array in order to find all the tiles that you need to draw, and you're going to iterate over that array like 400 times per frame, that's actually kind of slow just right there. So I started RLEing the tile map and things like that so that I could get through that particular operation faster. But once those sort of easy optimizations are out of the way, this actually works pretty well. You still are calling, in the worst case especially, a lot of OpenGL calls. But it does draw, and it does draw pretty fast in this sparse case. The nice thing about this approach is that if your tile map is sparse, like those layers that I just showed you were, it doesn't actually have to do a lot of work. It kind of has to do some work to figure out which tiles to draw, but the actual number of draw calls is fairly small. So that was good. The problem is, the worst case from this is really bad. You go up to like 9 to 13 milliseconds just to make the calls, and then like 19 to 23 milliseconds to draw, which is completely unacceptable for a game like this. When both layers are totally full of tiles, then you make a huge number of draw calls, and that gets up really slow. So then I went back to the meta-tile approach, but instead of drawing with draw texture, I decided to use VBOs, which I know are technically slightly slower than draw texture, but I figured maybe in this case I could come up with a way to use them that is a little bit faster. And what I ended up doing is I ended up splitting the level into what I call these meta-tiles, which are basically just this like regular grid of tiles that I define with verts. And then I just UV the atlas texture to them so that they look correct for whatever the level says they're supposed to be there. And I split them such that they're about, in that level, they're probably about 5 tiles wide by 5 tiles tall. I just want to get about 4 of them on the screen. So there's some pretty simple algorithm for taking the size of the screen and taking the size of the level and cutting it up into these meta tiles. And then the nice thing about that is that you only make like 4 draw calls per frame, right? You're only drawing 4 meta tiles. And it just happens that they're larger than the regular tiles. The other good thing is that you only have to call bind texture once for each of your layers, because, like I said before, state change is slow, but you're just going to bind this atlas texture once. It does take up more VRAM, but actually you have quite a lot of VRAM to work with on the G1, so it hasn't been a problem at all. The issue with this is it's actually not quite as fast as the draw texture solution in the previous slide in the average case, because being a sparse map doesn't give it any advantage. In a case where there's no tiles at all in an entire meta tile, I can throw that entire meta tile away. But in most of the cases, there's it's pretty common that you'd be in a situation where there are one or two tiles in there, and then you have to draw the entire meta tile. So the worst case and the average case are actually the same, which means it's a huge improvement for the worst case, but it means the average case is a little bit slower. Still, it's fast enough that I can probably get to 60 hertz from here. I'm only about 5 milliseconds away at this point. So this is what I ended up going with. Another way to do this would have been to maybe pre-render the level into like a canvas bitmap and then cut that up into different textures and then assign those to just very basic quads and use that. The problem with that is that it takes a lot of main memory, it takes a lot of VRAM, and the OpenGL startup and shutdown that I talked about before would become really problematic. So I haven't even tried that yet. It would probably render real fast, though. So I'm running out of time. Real quick, tips and tricks. You're making a game. You might have noticed you touch the screen, your frame rate drops. That's because when you touch the screen on Android, your application gets flooded with motion events. And the real easy solution we should probably solve this in the API, but for now the real solution is to sleep in the callback, because that will pause the thing that's generating the events and sending it to you long enough that your thread won't context switch so much and you won't get totally killed. You could start, there's a balance here too, right? Because if you sleep for too long in your input callback, then you're going to start dropping input events and your control is not going to feel as tight. But I think you'd probably get away with 60 milliseconds, 32 milliseconds, no problem, and that will pretty much solve that problem. You want to no longer see a frame rate effect of just touching the screen. If you're making a painting application or something, you might not be able to sleep for that a long time. The mechanics, like I said before, of loading OpenGL memory up and reloading it up when the context is lost are fairly complicated, but fortunately, there's this GL Surface View class that's in the API right now that does all this for you. So you use that as a reference or just build your game on top of that. I built my game on a modified version of it. This is just a real quick point, but ATITC texture compression is available on the G1, but you wouldn't know that unless you check the GL extension string. That's why you should check it. And you have to sort of find what the GL enum parameters numbers are and insert them yourself. But I've heard that because we're sort of bus limited in a lot of cases, that this can be a huge improvement. So if you're doing stuff with a lot of texture and you want to increase the amount of texture you can push over the bus every frame, you could look at ATITC compression. And then this is the bug that I talked about that Sprite method test separate from before I fixed it yesterday. And that's that including Cupcake, we failed to throw an exception when you use indirect buffers with OpenGL, which is actually against the OpenGL spec. And what can happen if you use indirect buffers is that the GC can move your memory around, and the OpenGL won't know it. So just use direct buffers. The API is almost exactly the same. It's pretty easy, and it will fix the problem. But in Cupcake, even right now, if you use indirect buffers, there's no particular error thrown. You might just get like a random crash. In Donuts, it will throw an exception. Okay, so game design tips, just Android-specific advice for making a popular game. Keep it small, right? When people go to delete stuff off their phone because they're running out of space, the applications get listed in order of size. The game that I just showed you, Replica Island, has like a bunch of different enemies. It's got 5 different like world maps, and it's going to have like 40 levels, and it clocks in at like 3 megs. So you can very easily if you choose the right kind of art style, you choose data that's easy to compress, you can make a game that is very small. Super Mario World runs in 512K. So you should try to optimize the size of your application because it'll increase your longevity. Make good games, right? The key to Android right now on the market is quality. If you want to get in that featured apps section, there's no way to do it other than making something that's really cool, that we at Google like, but also that all the users like. There's no way to pay your way in or have a certain number of downloads and then you get into something like that. Just make something that all the users like. So, I highly recommend that you put some time into polish, into making something that's really highly confident. And if you do that, you'll be ahead of the pack. Because there's a lot of people who just like to, throw something up there that they wrote in an evening, right? And the users are really, really picky. And they'll really prefer something that looks like it has a level of polish on it or has nice art style or something like that. So I highly recommend that you focus even a little bit on quality to set you apart. And then the last thing I just wanted to say, although I'm doing this out of order, is that not all devices are going to have the same input systems, and you should just be cognizant of that. I'm using a trackball for my game. I don't know exactly how it's going to work when the Samsung i7500 comes out, because that has a D-pad. Probably you should just support all of the input systems because they're already in the framework for getting events. But if you don't do that, you may have a game. Like, say you relied on the hardware keyboard for your game, it's not going to be playable on the Sapphire, right? So that's something else to be aware of. And that is pretty much my talk. Thank you very much for coming today. And thank you for listening, and I'm happy to answer any questions. Please use the microphone. Oh, I'm sorry. Okay, I'm going to answer one question, And then I'm out of time because I ran long. So I think you're up. What's up?
My question was about C++, whether game development on Android can be done in C++, and
Yes.
How easy is that to do, and whether there will be any sample apps for
Yes.
that platform.
Yes, can you use C++ for your game development? Right now, it's really hard. Very soon, we will ship something called the NDK, which will allow you to build C++ native components to your applications and call into them from Java, and then you can absolutely use C++ to build your games. If you do that, though, you're going to tie your games to whatever particular architecture you compiled that code for, which means that you're going to lose a lot of the interoperability that Android sort of promises. So if you're willing to make that change, or you're willing to compile for multiple architectures, then absolutely. And in fact, we have games up on market right now that are built that way. But as of right now, it's kind of a pain in the butt. Give us a little bit of time to build it. Okay, thank you very much. Sorry, just as you leave, if we can switch to this machine. Oh, I have it here, don't I? Here's the feedback link. Please go give your feedback about this talk and every other talk, because we'd really appreciate it. Thank you very much.